あ、テスト、入ってんのかわからない。ごめんなさい。
これを多分外で確認した方が。今ってこれ。
入ってる。
ちょっともうすぐ始まる。いい？今もう1分以内にチェックができる。いい？
ただいまテスト中。こっちからも流れてる。
じゃあ僕じゃこれ吉田さん今入れました。これ吉田さん。
So good morning, everyone. So it's a great pleasure to have this start It from Qubit school workshop in Kyoto, and welcome to Kyoto. And first, we'd like to thank for all participants and the invited speakers for coming all the way to Kyoto. And so we are very happy to have this to have so many people in audience, and so this event turns out to be very popular, and we got more than 400 applications. So that means we have to do some selection in the end. But still, in the end, this room is probably not enough to accommodate all people. So we are preparing these broadcasting rooms. So it is just next room is a salon, and also we have one more broadcasting room in second floor, Y206, just upstairs. And so we don't have enough space for this floor. So coffee breaks, we'll have it in second floor and third floor, and also another building called Moscow Hall. So we are sitting here, this auditorium, and we have coffee breaks on second floor and third floor of this building. And we can just go out of this entrance and walk to this Moscow Hall, just 2 blocks away. Moscow Hall? Yes. No, you. Thank you very much. Yeah, sorry, I should come. Moscow Hall, yeah. Sorry, yeah, unfortunately. Yeah, so and those who will get the reimbursement, the accounting office is here, this next building. And so there are general information that this is in this conference auditorium, please no food and no drink. And so for Wi-Fi, so please use antivirus software. And P2P, also P2P file sharing software is prohibited. And so we're going to have a poster session and gong show on each Wednesday, 19th and 26th. And the poster boards are now available in both places, Moscow Hall and Y306, third floor. So please just first poster presenter, please paste your poster there. And so we're going to have a banquet for participants. So for participants who register for banquet, please come to University Cafeteria in second floor. And finally, on Saturday, we're going to organize some informal excursion. But if you have a plan, of course, you can have your private tour. But we're going to prepare some file different tour. And in the morning, we have talks on Saturday, and afternoon, we have this informal excursion. And also secretariat desk, so we have many things to ask them. And Atsushi Watanabe and Asako Ando is there, so please ask them for administration, which is just the same floor and just room behind. And so accounting office for reimbursement is our next building, as I told you. So finally, so for regular registered participants, we have some small gift about this fan. Maybe this we can call it from Qubit fan, or maybe happy fan. So happy model is here. And so please, let's enjoy this exciting school and workshop. Okay, so let's start the first school lecture. First lecturer is Benny Yoshida from Perimeter. He will tell us about scrambling and related physics.
Okay, thank you very much for the introduction, and maybe we should probably, yes, so Okay, so yes, in these 3 lectures, I'm going to talk about quantum information scrambling. And maybe as you already know, quantum information scrambling has become a very popular research topic in many different branches of physics, like condensed matter, quantum information, and string theory, and more. So obviously, I cannot cover every material. So I will focus on quantum information theoretic perspective of this phenomenon of scrambling in these 3 lectures. And so if you are interested in gravity perspective, there is a very nice lecture by Douglas Stanford last year at IIS Summer School. And if you are interested in condensed matter perspective, there is a very nice lecture by Brian Swingle, I think last year in Boulder. But my main focus will be like quantum information scrambling. And that being said, for 3 hours, I'm going to cover some materials. And then normally I would spend like around 9 hours to cover these materials, but I have 3 hours, so I need to accelerate myself 3 times, but I will try. And please don't hesitate to ask questions. But let's get started. Okay. Okay, so I will talk about quantum information scrambling, and today's topic is the operator growth. And out of time ordered correlation functions. So now let me begin by giving you some idea of what is operator growth. So imagine that you have, let's say, 1D chain of qubits. So there are n qubits, then these dots. And assume that this system has some Hamiltonian, let's say local and then nearest neighbor interactions, and then we assume that this Hamiltonian is some generic interacting Hamiltonian, whatever it means. And then now imagine that there is some local operator, let's say W, acting on this qubit, some single qubit. We can assume that this is a Pauli X or Pauli Y or Z operators if you want. Then let's ask, like in the Heisenberg picture, this operator becomes time evolves like this. Of course. And then by operator growth, we want to study how this operator evolves in time. And of course, there is a very famous formula which is called Baker-Campbell-Hausdorff formula, which tells us that asymptotically this should look like this. So this is the first order term, and then the second order term, and then second and then third order term would be something like this. So there are 3 H's. And it keeps going. So now, if we do this, then we can see that indeed the sort of the size or the weight of this initially local operator growth under the time evolution. Namely, in order to see this, we just observe that. So initially, we had local operator W. So this is W. But the second, the first order correction contains this commutator between H and W. Now, since H is a two-body operator acting on 2 sides, so if you think about the commutation between H and W, you will get the big operator, and that is some operator supported here, here, here. So initially this is just one body operator, but this becomes a two body operator. Right? So it's slightly bigger. So originally it was supported only here, but now it's supported on this region. Now, if we keep doing this, then of course so in the first, second, third order term, this will be actually a three-body operator, and it's supported on these regions, and then keeps going. Okay. Now, when t becomes larger and larger, so when t is 0, of course, this is the only contribution, but when t becomes larger and larger, these higher weight terms becomes more dominant, and then w operator becomes bigger and bigger. So this WT operator becomes very large. Okay. So when we study quantum information scrambling, actually this notion of the operator size growth plays a very important role. And in fact, you can give a precise definition of scrambling by using these notions. But so with these observations, I guess it's pretty obvious that the size of the operator will keep growing for generic interacting Hamiltonian. But this large is not well-defined term. So let's make this intuition more precise. So in order to discuss how large operator is and discuss the size of the operators, we need to define some unit of sizes. So in order to do that, we need to discuss the basis operators. Here, so in this lecture, because we are dealing with qubit system, I'm going to use Pauli operator as a basis. If you are using fermions, you can use Majorana operators. So the Pauli operator in a qubit system, n-qubit system, consists of the following tensor product of local Pauli operators. And maybe another example would be so it's just product of local Pauli operators. So at each qubit, you have choice of I, X, Y, Z. So if you have n qubits, there will be 4 to the n operators, including identity operators. Now, given these operators, it turns out that these Pauli operators form a complete basis of operator in the following sense. That is, given any operator acting on any qubit system, let's say WT, you can always expand it by using Pauli operators. Okay, like this. So I'm not going to do this expansion. Okay. So P is the Pauli operator of these forms, and then alpha P is just some coefficient. Now, in order to derive this alpha P coefficient, you can just use the following orthonormality conditions for the Pauli operators, which goes like this. So it's actually Pauli is Hermitian, so you don't need dagger, but in generic cases, it's better to put dagger, so I'm just keeping dagger. Then this, so this orthonormal conditions hold. That is, if you multiply different Pauli operator, then you will get some other Pauli operator. But the trace of the Pauli operator is 0, So when P and Q are different, you get 0. But when P and Q are the same, then you will get identity operator. Then the trace of identity operator is same as the total Hilbert space dimension of the system, which is, in our case, 2 to the n. Okay. Now, by using this condition, the orthonormality conditions, you can solve for alpha p. And then that's, well, you just use it. And then what you get is right? So that is, you just multiply this equation with some Pauli operator P and then take the trace. And then you will get this equation. So maybe I should help. Okay. So in principle, if you know how this WT operator look like, you can just compute these quantities and then look for the coefficient. Or, yeah. And then more in a physical term, this quantity alpha p is related to the 2-point correlation function of the system. Right? Where the quantum state we are looking at is actually a maximally mixed state. Okay. So if you want to study the operator growth, in principle, by computing this 2-point correlation function, 2-point time-ordered correlation function, then in principle you can do the experiment and then compute alpha p, and then you can characterize WT, the time-evolved operator, completely. Okay, that's of course possible, but in reality, this alpha p is very, very small number. It's usually exponentially small in the size of the operator, so it's not a physically interesting quantity or meaningful quantity. So then we will see that out of time ordered correlation function is actually better suited for studying the growth of the operator size. Anyway, so I have introduced the basis operators and expanded it with these guys. And then you can see that this kind of resembles you have wave function and then expand wave function with basis vectors like 0, 1, 2, and so on. And then in fact, you can extend this intuitions further. And then in fact, very important property of this representation is that if this WT operator is a unitary operator, then it implies that the sum of the coefficients squared is always equals to 1. And this can be derived by using unitarity, that is W dagger times W is equals to identity. So you can just square this and then you can derive this. But the important observation is that, of course, this alpha p square can be interpreted as a probability distribution. Probability to have Pauli operator P. So this basis expansion works in exactly the same way as the, well, when we discuss pure state of the quantum state. Now, given this basis,
so this interpretation is a bit confusing because the total dimension is 2 to the n, while there are 4 to the n operators.
Right.
So
it's actually, I will discuss in what sense that is a state. Yes.
Yeah, the state, there are only 2 to the n states.
So it's actually, there is a given operator, you can map it to a state, and then that can be done in a doubled Hilbert space always. Okay. So H, then H times H. I will come to that. Okay, so this is how you expand the basis. And then with this basis, you can define the size. And then I will just write down how it would work. To define the size, you look at the time evolved operator and then sort them into the following way. First, we will look at the zero-body Pauli operator. Well, zero-body Pauli operator means just identity operator. It's like no non-trivial support. And then there's a coefficient for that. And then there's Pauli operator, which is one body. One body Pauli is like x1, y2, z3, and so on. That has only one non-trivial support. Then you keep doing this, and then eventually you have n-body Pauli operator, where Pauli operator has supports everywhere on your qubits. Then, of course, given this, I want to say that this operator has size 0. This one, size is 1. This one is size 1. So the average size you are observing in this time-evolved operator could be defined in the following way. That is K. So I'm basically summing up all the probability distribution to have K weight operator or K body operator. Then that goes like this. Right? So this is the summation of a K body operator. So this is the probability distribution to see K body Pauli operator, and I will put K weight and then define the size. So this would be a kind of proper definition of the size of the operator. Now, having gone through these formalisms, what we have right now is that we have a formalism to define the size of the operator. So we anticipate that well, if we use this proper definition of the size, and then if you look at the Hamiltonian, like interacting Hamiltonian, the local operator will be growing to bigger size. Now, I think it's better to give you some examples. So I want to show you one slide very quickly. And maybe you can switch to, yeah, how does it work? Yes. Maybe I shouldn't have written here, but.
Danny, while we're waiting, can I ask, in the pictures over there,
Yep.
you had a position, and it was important that we talked about growing around that. Whereas in your definition behind the screen now, that position doesn't seem to play a role. So
Right. So, of course, eventually you will be more interested in like where you have support, and then that can be studied by using out-of-time ordered correlator.
Okay.
But basically, what I want to motivate here is that we are interested in like distribution of the how big the operator is, where it's supported, and so on.
Okay.
It also allows disjoint several.
So that's one definition of size, but it depends on your interest. And so I want to show you this plot because I think it's better to look at actual example. So this example was studied in a paper by Daniel Roberts, Douglas Stanford, and Lenny Susskind in 2014. They looked at this particular Hamiltonian in 1D. So this is almost like an Ising model, except that you have HZ term, so it's a parallel field. So this H term makes the model non-integrable. So they have studied two cases. First case is non-integrable with H term, and then they choose this weird combination of the coefficient, and it turns out it's known in the literature that these combination kind of magic numbers, it makes the system more and more chaotic and non-integrable. But these particular values have no essential meaning. In the second case, they studied the integrable case, J is equals to 1. So that's the case where it is at the criticality of the transverse field Ising model. In any cases, we should really focus on non-integrable cases, which are given in solid line. Now, what they have done is that they have numerically did the exact diagonalization of this Hamiltonian. This is actually just an 8-qubit system. And then you start from one body operator and then time evolve it and then see how its size grows. And then here is the plot of the probability to see one body operator, two body operator, three body operator, four body operator, and so on. So these are the 1, 2, 3, 4, 5, 6, 7, 8. Of course, when time is equal to 0, you only have one body operator. So this starts from 1 unity. But after the time evolution, you see that the one body operator quickly disappears and then becomes very, very small weight. And then this two body operator kicks in, which means that the one body operator has grown to two body operator. But then after the time evolution, you see that the three body operator weight increases. So two body operator grows to three body operator. Then three body operator, four body, 5, 6, and 7, and then eventually it becomes 8 body operator, the very big operator. Now you can see that from this plot, indeed, this operator size should be growing, growing, growing. And at late times, let's say after this time 4 or 5, you see that the probability distribution of the weight of the operator gets saturated and then doesn't move much. Okay. So at late times, you would observe 8 body operator with this probability, 7 body and 6 body and so on. So that's actually, I need to look at their paper again, but I'm pretty sure they have looked at well, one of the Pauli operators. Yeah, sorry, I forgot which one was it. Yeah, but any one body operator. I believe it was open boundary condition.
To what extent is this notion of size basis? Oh, to what extent is this notion of size going to be basis dependent?
Basis dependent.
Right. I mean, it seems to depend on the choice of Pauli's.
It's not basis dependent at all, in a sense that what is important is we have qubits that defines your tensor factorized Hilbert space, qubit 1, qubit 2, qubit 3, and so on. Then given this basis, it's not that important which basis operator you use. So we have decided to use Pauli as a local basis to span each qubit. You could use some other basis operators, which would be as good as Pauli, so that's kind of rotated from Pauli operator. As long as you have the same tensor product structure, that is fine.
But would I imagine getting different saturation values, or would it really be exactly the same?
Oh, it's just exactly the same.
Okay, great, thank you.
It's basis independent. Yeah. If you respect the same tensor product structure.
If instead of qubits you had qdits where d was large, then you might have to worry more.
Yeah. But first I define the tensor factor and then start doing that. And then as long as I have well-defined tensor factors, and then yeah, I can define the size with respect to qubits. Yeah. In that sense, it's basis dependent in a sense like it's qubit or qubit dependent. But yeah. Anyway, so it's actually, this is a very fun example to look at and to build intuitions. So yeah. Anyway, now this is the only slide I need. Okay, so as you can see in this plot, well, operator size seems to be growing, and then it becomes bigger and bigger and bigger, and then once it becomes big, it stays very big. So I want to make two very brief comments on this. Should be very brief, so 2 remarks. First is so operator has a tendency to grow. That is, if you start from a local operator, it should keep growing unless your system is an integrable system. And this seems to be a very robust feature of interacting Hamiltonian. And then in this talk, in this lecture, I'm not going to talk about gravity physics much, but people think that this tendency to grow is related to some physics that is a particle falling into a black hole. In areas CFT. Very intuitively speaking, if you have a particle outside the black hole, it will be pulled to the black hole. It keeps falling into the black hole. That's there is a preferred direction. And then this direction, or the fact that it should be pulled toward the black hole, can be actually associated to the growth of the operators that needs to keep growing. The size of the operator does not decrease. So that's one kind of motivation why we should be really studying this operator growth or scrambling phenomena. And the second comment I want to make is that, well, I will keep this very brief, but the difference between entanglement growth and operator growth. So I have discussed how the operator becomes bigger and bigger in these interacting systems, but traditionally we have looked at how the entanglement grows in a system. So the point is that these two concepts are different things, but let me just simply explain very briefly why they are different. In entanglement growth, we typically, the problem setting would be the following. We start from some state, such as O0 state, like a product state, which has no entanglement initially, and time error the system by using some Hamiltonian. Then the system is cut into two parts, A and B. Then you can study how the entanglement entropy, entanglement between A and B grows in time. And obviously, well, at the beginning, there's no entanglement between A and B, but as time evolves, these two subsystems become entangled. And then you typically see some plot in the literature. The entanglement entropy on A keeps growing in time and then gets saturated. So this is, roughly speaking, what we call entanglement growth. On the other hand, the point is that, well, operator growth is different in a sense that entanglement growth usually starts from this very special state with no entanglement. It's a very special state. But operator growth, the quantum state we are interested in is implicitly a thermal state, namely this maximally mixed state. So of course you can discuss the case where this is a thermal Gibbs ensemble, but the point is that this is a maximally mixed state. So in this sense that when we study operator growth, we are not thinking about this special state, like with no entanglement state. What we are looking at is a kind of a mixture, a thermal mixture of all the states. So we are interested in more of the average properties rather than the properties for the particular quantum state. So I could maybe I should spend more time on this, but I will just make one comment that is this famous Lieb-Robinson bound. Is more suited to study this entanglement growth because this is a bound, it's a one norm, so which is looking at particular state, whereas this operator growth, we usually look at the thermal state. And that is actually reflected to the fact that this operator basis expansion is related to a correlation function given for the thermal state or the maximally mixed state. So that the point is that they're different things. Okay. Okay, cool. Yeah.
Yeah. About your first remarks, so the operator also grows very large because it grows from a very local operator. It's still just, it doesn't change the state dramatically. Is it?
The state.
Yeah, because for example, like the energy won't change dramatically, the charge won't change dramatically. But
Right.
for a particle falling to a black hole, will it change the geometry
So this
dramatically
is in
due to the blue shifts?
yeah. So this is in the fake the ADS-CFT correspondence. So that is I'm looking at the Hilbert space, which is the outside, right? So then I have some well-defined Hamiltonian, and then I create a particle by perturbing this system a little bit. So the total energy defined on the boundary is unchanged, right?
I see.
Yeah.
Is there a sharp distinction between gapped and gapless Hamiltonian in this
This phenomenon. I would say that, well, empirically, I would say that the gapless system scrambles more. But, well, yeah, that's,
Okay.
I am not aware of any kind of universal explanation relating to gap and gaplessness. And
Thank you.
About the entanglement growth, why do you have saturation of entanglement if you just divide your system into parts? Is that correct picture for this type of quench?
it's generically true in a sense that if the Hamiltonian is non-integrable, yes, and I believe that that's something you would probably be able to derive by using ETH, like eigenstate formalization hypothesis. You mean this one, right? Yeah.
Yeah. Okay.
Yeah.
Thanks.
So this is pretty, I think, generic. That if you start from, I mean, we usually get formalized, right? Yeah.
Thanks.
Oh, the maximum amount. I really don't want to go really into details of this, but it's just related to the initial energy you have. So here I started with 0,0000 state, and this has some energy density, like energy expectation value with respect to the Hamiltonian. Then usually the entropy is related to the thermal entropy that you would see in this region. That is, yeah. But if you just pick some particular random state here, then the chances that well, this is close to the size of the A.
Thanks.
So does the deep Robinson bound also characterize the time of growth of correlation functions?
Correlation functions, right. But the point is that, well, Lip Robinson bound is, this bound is one norm bound. So you one in the bound. That means that you are mostly interested in some particular state, not an ensemble of states. Yeah. Anyway, so I just wanted to remind you that the Lip Robinson bound looks similar, like the commutator and so on, but the physics we are looking at is quite different. Anyway, so so far I have told you that well, operator should be growing, and we somehow want to study it. And it turns out that well, as I briefly mentioned, that you could study the operator growth by looking at this two-point correlation function, but alpha p will be very small because it adapts to 1, which means that there are like exponentially many Pauli operators. So each of them should be very small. So this is not a good correlation function to look at. And then it turns out that the right thing to look at is the so-called out-of-time ordered correlation function. This is sometimes called OTOC. And the definition would be like this. So you alternate and look at this quantity. So V is at 0 time, and then W is at t, and then you repeat this. So it's out of time ordered. So, and then for us, this can be explicitly defined in the following way. That is trace of this operator when divided by d. That is because we are mostly interested in the maximally mixed state. Okay, so this is the definition of out of time ordered correlation functions. Now, the reason why this quantity is interesting is the following. Imagine that you have a game, this 1D spin, and so qubit 1, qubit 2, then there's nth qubit. Now, let's take B0 is this operator acting on first qubit. Then let's take this W0 at the, let's say, the other end of the spin chain. And under the time evolutions, this W0 operator becomes bigger and bigger, and eventually it covers the whole space and becomes as big as the whole system size, and it starts to be overlapping with W and B0 operator. Now, but at very early times, since there is no overlap between WT and W0, so this weird ordering of the operators, 0T, 0T, does not matter because they commute with each other. So at early time, this out of time ordered correlation function is just equals to the, you can actually swap these two operators, and then these operators, if W and V are unitary operators, they cancel. So it starts with this big value 1, initial value, and it stays there for a while. But once this WT operator, the support, hits this qubit 1, then this value starts to decay from this one. So T late, then this auto will become small. That is our intuition. Okay. So then with this out of time ordered correlation functions, we would be able to see that whether this WT operator has support on A and qubit 1 or not, right? So this is the intuition. Okay. Now I want to make this intuition more precise. By explicitly showing the relation between the size or the support and the out of time ordered correlation functions. Now, again, let us look at WT operator. Then here I'm interested in whether this WT operator has support on qubit 1 or not. For this reason, I can expand WT operator in the following manner. I times P means that I acts on the first qubit, so this operator, this Pauli operator has no support on first qubit. So that's operator which looks like this, so big operator P. So this is first qubit, and then there's a coefficient. And then next you can look at Pauli operator, which acts as X on the first qubit. So that is this. Then you can do the Y and Z in the same manner. I'm not going to write it down, right? So then, with this decomposition in mind, you would say that this operator has no support on first qubit, whereas this has support on qubit 1. So when we say that whether WT is supported on the qubit 1 or not, we are interested in the total amplitude of these guys. So from this observation in mind, we could just define this amplitude as probability to have identity operator on the first qubit. Then these amplitudes as a probability to observe X operator on first qubit, Y and Z in the same way.
So if you are interested in evaluating this, why do you consider 4-point function rather than 2-point function?
Yes, that I didn't mention, but the point is that if you look at the 2-point correlation functions with respect to this thermal correlation function, like W0 and B0 and WT, it's very small in a sense that it's just this quantity, alpha p, which is exponentially small in the system size. So if you can...
Not positive. Oh, okay.
Yeah, because this alpha p squares and then it should add up to 1. So it's very small quantity. So you could compute it if you are very careful or, I don't know, numerically. But in reality, it's not that good because it's the same as seeing nothing. Whereas this out of time ordered correlation function, we know that it starts from 1 and it decays to small value. And then any decay from the initial value 1 would signal you that there is a support. Yeah, that's if I have time, I will mention that. Yeah. Where am I? Yep. Yes, so we are interested in the support on qubit 1. Now, the total probability to have support on the qubit 1 would be can be, of course, written in the following way. That is a probability to see X, probability to see Y, and then probability to see Z. I mean, you might think that this expression looks very basis dependent, well, depending on your choice of the operators, but it turns out that it's not. And if you write it in this way, it's actually kind of clear. That is, probability of observing 1 is a basis independent concept. So it turns out this combination is a basis independent quantity. Anyway, this is the probability to have some non-trivial support on qubit 1. Now, having defined this quantity, there is a very useful formula or theorem or whatever. Let me use theorem because this is actually a mathematical formula. You can derive is the following. So it's a summation over all the one body or zero body, like all the Pauli operator acting on the qubit 1. Then you compute the out of time ordered correlation function. Okay, so this is the out of time ordered correlation function, and then we are interested in the growth of this WT operator. Then let's just study out of time ordered correlation function where V is taken to be X or Y or Z or just identity operator that is acting on the very end of this spin chain. Now, if you compute this quantity, it turns out that this is equals to probability of seeing identity operator on the end of the spin chain, which means that this is 1 minus kind of support. Now, I guess this formula makes our intuition more precise. That is, out of time ordered correlation function is a good probe of the size or the growth of the operator. As I said, this autorq initially at t equals 0 is 1. So 1 means that there is no support. So support is 0. But at late times becomes small. I mean, small means, well, how small you are interested in is that matters, but small. This means that this support becomes larger than 0. So you have some non-trivial support on the qubit 1. Now, I don't know how I'm doing in terms of time. It's okay. So I was originally planning to just derive this quantity, this expression, but maybe I can try. I mean, if this formula is obvious for you, I can skip. But so let me give you a kind of sketch of the proof or derivation. So now, first of all, computing this quantity, I'm taking v as I, x, y, z. And also for the w, there are 4 contributions. The one that is identity operator here, x, y, and z. So in total, there will be 4 times 4 in 16 kind of combinations of the terms you need to look up. So let me create some table. So on this side, I put the B0 operator. The choice was I or x1, y1, or z1. Each of them appear with probability 1/4, right here. On the other hand, I'm looking at also WT operator here. It has 4 kinds of contributions: I times P, X times P, Y times P, Z times P. Right? Then each of them appear with a probability distribution which look like prob I, and so on. Okay. Now for each combination, you need to compute the contribution to this out of time ordered correlation function. Now, there are several easy cases, but let me first, so here, let me just look at these 2 parts, and then what the contribution is. So when V is an identity operator, and WT is coming from this type of operator, I times P, then you see that this W and the V operator, of course, commute with each other because you have same thing. So it's just this weird ordering doesn't matter, and then you can swap it, and then the contribution to out of time ordered correlation function would be 1, right? That's because these 2 operators commute. So we could put 1 here, operate the same way. Then it's actually 1 and 1 here, and so on. So this is how you can see this. On the other hand, let's say we look at this contribution. For this one, V is x1, so like this one body operator acting only on first qubit. And the WT would be y times some Pauli operator. Then if you look at this combination of operators, you see that they do not commute with each other because you have x and y. And since x and y do not commute, it's anti-commute. So if you compute the contribution to out-of-time ordered correlator, it will be -1. It's just anti-commutation. So I should put -1 here. Then I can keep doing this for all 16 components. And then what I get is the following. Well, you just look at the commutation between these parts and these parts and so on. So it's actually pretty easy to do that. Okay, so this is a table. And then the point is that this contribution appears with 1/4 times probe x, 1/4 times probe y, and so on. So you can just add up all of these with these coefficients. Then if you do that, then yeah. Then you see that all of these contributions for, let's say, probe z disappears because it's 1 minus 1 minus 1, so it adds up to 0. So this term will be cancelled, this term will be cancelled, this term will be cancelled. So you only have probe 1 as a contribution. So that's the reason why this left-hand side is exactly equals to probe 1. Okay, anyhow, this theorem or formula just tells you that the smallness of an out-of-time ordered correlator would tell you whether your WT operator has support on this particular qubit or not. Here I'm focusing on the support on qubit 1, but if you compute the same thing with qubit 2, qubit 3, qubit 4, then you can basically create like a kind of a complete data of your support of the operator, whether it has support on 1, 2, 3, 4, and so on. And from this data, you can easily compute the total size of the operators. Okay, so that is the reason why this out-of-time ordered correlation function would be a very good measure of the operator size. Actually, I would encourage you to actually verify this kind of a formula or relation by using actual 1D spin chain. It's actually very fun, and it's very useful to build your intuition by doing some exact diagonalization. Okay, so this is why OTOC is related to operator growth. And then, okay. Now, I guess I want to change the topic a little bit and then revisit these problems. That is partly because originally this lecture was titled Quantum Chaos. So I should mention why this operator growth is related to the quantum chaos. In order to do that, I need to talk about what we call the operator state correspondence. This is actually related to the question Hiroshi mentioned, that there's the Hilbert space of the qubit is 2 to the n, while when we expand this WT operator, we use a 4 to the n operators. So this number doesn't match. Okay, so in order to understand this very properly, we should introduce what people call the operator state correspondence. And this is actually particularly useful concept in studying scrambling phenomena. So let's just consider a V, it's a unitary operator. Well, WT or V, whatever. This is a unitary operator defined on Hilbert space H, which is a 2 to the n dimensional Hilbert space. The statement is the following. Given unitary operator on H, you can always find the corresponding pure state, which I write in this way. That is supported on H times H, so double Hilbert space. So the point is that this operator was supported on 2 to the n dimensional Hilbert space. Now this pure state representation is supported on 4 to the n dimensional Hilbert space. Now, how do we define such a corresponding pure state? Well, in order to do that, you expand unitary operator in the following manner, like blah and ket. So this is a definition of the operator. To define the state, you can actually do this. To define the state, it's very looks like this. Okay, so I just flip the blah or ket blah to ket and then put tensor product sign. I need this normalization factor in order for this to be properly normalized.
In this case, it does seems to depend on the choice of basis.
Which one?
The choice of to define the pure state V. We need to choose a basis of the Hilbert.
Oh, it's actually, well, that's good. No, I don't think so. But well, it depends on your. So this is the definition, and it's defined in a state-dependent way, but as a basis-dependent way. But actually, equivalent way to define this wave function is the following. You define the EPR state in the following way. J and J. And then this quantum state V can be written in the following manner. That is, you prepare EPR state pair and then apply unitary operator V on the left-hand side of the EPR pair. Now, although this definition looks basis dependent, it is not really basis dependent. The reason is the following. The definition by EPR pair has this J and J labels, which is written in the basis dependent way. But you could just use another basis, let's say J prime, which is unitarily related, but any arbitrary basis. You actually need to put complex conjugate to be sure, but
Yeah, but that's the whole point. That's the whole point. Is that
If you
complex
can do
conjugate.
that, then it's basis independent.
You secretly have some anti-unitary operator in mind here that you've chosen.
no. This is always true.
No, you have to put star on the other side.
No, when you're defining a map, because that first index on V in the operator is like a thing that multiplies a ket, it like runs over kets. But in the second line, it
Maybe I should be.
Map from kets to bras.
Yeah, so all I'm saying is that given a complete basis, you can always do this.
Yes, that's right.
Yeah. So in this sense that it doesn't matter which basis you expand.
You should have used that notation over
Why
there.
didn't you put the star up there, though, right?
Yeah.
The star should be in there, right?
Right. Yeah, I think that definition.
I'll be happier if you put a star there, but then you have to define the star.
Wait. Well,
I agree.
no. I define J to be like basis, like 0, 1, 2,
That's
3.
why I said it's basis dependent.
Yeah. And then no. Of course, you could put star
So
here.
what does that mean? What does it mean to put a star on an integer?
Yeah. So star.
Does it secretly mean there's a unitary?
Yeah. So this is a very special state which has all real
Yeah, that's what but that's what I meant by basis dependent.
Oh yeah. In that case, yes. But the point is that EPR pair can be written in this way. So in that sense, it's not basis
I mean,
dependent.
it's not totally trivial. Like people say wrong things about the thermofield double because they don't understand.
Yeah. That's sure. So it's actually very important to have star here.
Yeah.
And yeah. Yeah. So, but anyway, yeah. But yeah, sorry, I don't. Anyway, yeah. So whatever it means, like to the extent that the EPR pair is state basis independent, it is independent. So actually, I'm not sure how I'm doing in terms of time, but. The reason why I wanted to introduce this formalism is that I can represent out-of-time ordered correlator by using this state representation. So out-of-time ordered correlation function looks like this. The time goes upward, and then there is a trace. So trace, and then you have a coefficient 1 over d. So this is a definition of our out-of-time ordered correlation. This is, of course, defined on a single Hilbert space, H. But you can actually pretend to interpret this guy as a function on the double Hilbert space, which can be done in the following way. So this is the first Hilbert space and the second Hilbert space. And here you put EPR pair. So this EPR pair carries the following factor. So the factor matches. And then, so the point is that I just expanded this, put this line, and then define like this. But the point is that in this double Hilbert space, you compute this operator identity on this side, and then compute the expectation value with respect to the EPR state, and the same thing. So I haven't done anything fancy, just this. But given this representation, you can further make the following transformation. Okay. So it turns out that these two things are the same, meaning that acting on W Dagger operator here is actually same as acting W star operator here. And then actually in order to go from there to here, you need to be very careful with this complex conjugate of integer. But you can play the game. Yes, and then so you put star here because of this subtlety. And anyway, so this is, but all I did is I just pulled this operator along this line and then put it here. So I haven't done anything fancy yet. But if you look at this interpretation of the out-of-time ordered correlation function, then initially this was an EPR pair. Now what is this operator? That is V times I times EPR. Right? So this is exactly the V representation we had. This is the same V Dagger. So this is actually the bra of the key. So the result we can get is the following rewriting. That is, out-of-time ordered correlation function defined on a single Hilbert space is equivalent to 2-point correlation function at time t computed with respect to state representation of V. Okay. Okay, so this is mathematically cute, but I think this is nice because you can see the relation to quantum chaos or black hole with this representation. So EPR pair times V. So again, in this time flow, so I'm just drawing the same thing. Initially, you have EPR pair. So this is EPR pair. And then suppose that this V is just actually an identity operator. That is, you didn't do anything to the system. And then you time evolve the system. Then, of course, you still have the EPR pair. And then you measure the two-point correlation function, W and W star. Then you will get 1 because there is a EPR-like correlations, and W times W star will see this quantum entanglement between left and right side. So that is the case where V is equals to identity. But suppose that V was not an identity operator, something else. Then initially we had the EPR pair, but initial state has some small perturbation added. So it's no longer the EPR pair. Okay. Then we time evolve the system. Then this correlation function still try to verify the quantum correlation between these two sides by measuring W and W star. But the point is that when out of time ordered correlation function is decaying, this means that this correlation function is no longer 1. So this was initially 1, but at time t is smaller than 1. So what does this mean? Well, in studying classical chaos, what we usually do is that we prepare two identical macroscopic objects, and then we time evolve them in the same way. Okay. Then, of course, the outcome should be the same. But suppose that there's some small butterfly was flying or whatever, that is this V, small perturbations, and then two same object time evolve in a slightly different way, and then in the outcome, at late time, you would see the difference, which is kind of amplified, exponentially amplified. That is butterfly effect. But in quantum situations, here what out of time ordered correlation function is looking at is the following. Instead of two identical objects, you are preparing two macroscopic objects which are entangled with each other. EPR pair is actually one particular way of realizing this situation. So you have an entangled state. Now your quantum butterfly or whatever flies here, just tiny effect, then time evolve it. Then no matter how small this effect is, at late times, you see the difference. And then in quantum case, it was originally EPR-like entanglement. At late times, they are still entangled, but their entanglement structure changes. So. Late times. And then what we are observing here by out of time ordered correlation function is how this structure of a quantum entanglement has changed. That is entanglement between a correlation between W and W star decays. So in this sense, this is a kind of nice generalization of the notion of chaos or butterfly effect we are seeing. And in the black hole physics, this EPR pair will be replaced by two-sided black hole, which are entangled with each other, and then you add perturbation to one of the black hole. And in the case of ADS CFT correspondence, more generically in black hole cases, the small perturbation becomes a shock wave, and then there's actually a way to do the bulk computation to compute out of time ordered correlation functions. But the point is that what we have in computing out of time ordered correlation functions, it is related to the growth of the operator to bigger sizes and sizes. This can be interpreted as a change of the structure of the quantum entanglement seen from local operators. Okay, so yeah, sorry, I think I went over time. So, but that's the end of the talk. So, so in the next talk, I have been talking about formalisms, and then I haven't actually discussed any concrete time evolution which makes this phenomena possible. And then in the second lecture, I will discuss what is called the Hall random unitary operator, which sort of exhibit these properties in the strongest form. Okay, anyway, thank you very much.
Thank you very much. It was a very interesting lecture. So we can take a few questions before the break. Any question?
Okay, I have one question. So here you defined the quantity of the operator growth by spin system. So how will you define such property for some, for example, oscillator system, or for some field system such as scatter field or something?
Okay, oscillator system. Yes. So actually, it's more like an advertisement of our work, but we have written some paper which studies operator growth in the oscillator system, like bosonic system. In boson system, you have nice basis operator, that's displacement operator, and then you can sort of expand your growth of the operator by using this displacement operators. So that can be done. Although these systems has divergences because it's infinite dimensional. So you need to define the size and so on with respect to the state you are interested in. Here I'm looking at maximally mixed state, this identity operator. But in the case of field theory or oscillator, this I is like infinite. Yes, and then you need to define these things with respect to this. But that is doable, and then, yeah.
Okay.
Yeah.
Could you explain what does it mean by put a star on the integer? What's the physical significance of
Yeah.
Heating time on the two sides of the universe runs oppositely. Are they related?
Yeah. Yes, in the sense that in two sides of the, well, in ADS CFT two-sided black hole, left-hand side time evolves with U, and then the other side should time evolve with U star. So it should have the complex conjugate, and then the reason is that, well, yeah, this is always true for any unitary operators. And well, that's sort of important here in this characterization of the scrambling, or the quantum chaos. That is, this time evolution is like keeps this invariant, but right. But I define the EPR pair by using particular basis, which is satisfies this definition. But you could just define it in this way. Yeah.
Maybe one more last question. The last question.
The sort of out-of-time ordered correlator that you have explored is the kind that arises from, for example, a square of commutators. So I was wondering, in general, one can have a wide variety of out-of-time ordered correlators. And I was wondering whether all these correlators show the same behavior in terms of the kind of growth that you mentioned.
Right. So I don't know what you mean by various form of
Various orderings for various time orderings.
I see. I believe that it's very important to have this out of time ordering. If the operator ordering is forward, like 0, T1, T2 in going time, then what you would see is usually the correlation function will be decomposed into product of each time. So then you don't really see the growth of the operators when you compute this quantity with respect to thermal state. So this out of time ordering seems to be very important.
No, what my particular question was that the out of time ordering can be many different kinds.
Oh, right. That way. Right.
I mean, this is vastly larger than ordering. I mean, for n points, you can have, let's say, n factorial way of ordering. So, are all of them equivalent?
No. They are not equivalent.
So, what drives us to some particular choice over something else?
Like, for example, you could try to study, so this is like past, future, you could do this many times. And then there are some physics you can probe by doing this higher point out of time ordered correlation functions. Now, there have been such studies in, let's say, ADS-CFT correspondences. And then, but in terms of the growth of the operator in a coarse-grained level, I would say this 4-point correlator is enough to see the physics, but there could be some fine-grained chaotic properties that can be probed by higher point out of time ordered correlation function. So the simple answer is I don't know. But 4-point correlator is pretty strong enough to see a very interesting phenomenon.
Thank you.
Okay, so let us page again. So we will come back at 11:10. So we have a little bit enough time for coffee break, 11:10. And the coffee break place, as I announced, is the second floor and third floor of this building or this mascara hall, which is 2 blocks away.